It's like most of you are going ahead and chatting me your first and last names. I appreciate that. Oh, here comes the yawns again. Feel free to ask questions. We've got 4 or 5 minutes before class starts anyways, so ask away if you so desire.
I had a question about the homework, chapter
Okay,
7. When
gotcha.
you were in class on Wednesday, I thought you had said since the test was due on Sunday, this chapter 7 homework was due on Tuesday.
Yeah, it was. I evidently neglected. Either I neglected to do it, but I thought I remembered doing it, or I might not have hit uh the submit button twice. It's a multi-button process, so I think I might have just did it by accident. I literally just changed the due dates just now, like
Oh,
five
okay.
minutes before I got in, but I noticed they were wrong. Let me double check what the dates are now. I actually have that open, I think. Oh, no, I don't have it open. Crap. It's kind of hard to get there, but if you find that they're not set properly, let me know. But I think what I did is I moved everything till tomorrow. I believe that's what it is. If you need more time, let me know. I could probably give you at least till Sunday of this weekend.
Um, if so you said when we first started this class, didn't you say that if we logged into Pearson on our own and did the homework, you're not going to get it right? We have to go in through Canvas?
Yeah, that's the downside is you got to go through Canvas. If you find a way to go there and you've used it, let me know because I'm curious to see if they fix that. But they literally originally told me that never ever ever let any student go on from the internet instead of through Canvas because if they do, it'll block me from getting their scores. So if you did that in a attempt to get by, just let me know so I can watch and see if your grades are updated like they're supposed to.
Uh,
But
I I missed the Canvas thing because I actually couldn't figure out how to get through it to Canvas. I've just been typing in Pearson and just going by the link in the history one. My grade's been going through.
let me double check that right now. Actually, I got enough time. I think I can go ahead and just do it. Let's see here. I have to go back to the other course. I'm on the website for mastering right now, and you're 241 N02B, and you're Colin Bryant, right?
Yep.
So let's see. So first, what I'm going to try to do is I might not be able to see it because I might not be able to access the part of Canvas that I want. But the good news is your scores are definitely in this grade book within mastering. It's just a matter of seeing whether it's actually going to be in Canvas, and I don't think it. Nope, it's still not letting me get there. I thought if I went in there's another way I can get in.
I've seen them on my end on Canvas. I just wanted to make sure it was
Oh yeah,
actually
if you see
working.
it on your end, then you're golden. So it
Okay.
evidently they might have fixed it. So that's awesome. Glad to hear
Okay.
that. Appreciate you letting me know. That's awesome. I have to sort of black box some of the handshaking because it's stuff I haven't been able to afford the time to learn, and I write pseudocode for them for various jobs, but I haven't done anything of the IT side or the networking side. Yeah. So yeah, everybody, if you have seen your grade actually in the Canvas grade book, then whatever you've done's been fine. It should be updating, and I keep clicking. It's got an automatic update refresh or whatever. So that should be going through automatically. The only thing is I have to add new chapters as I cover new chapters. Uh, if I did them all at once, you'd see all the dates and they'd all be screwed up, and it's just a weird thing. So I've been keeping it where, as I start a chapter, I open the chapter and try to set the due dates. So hopefully that works. Looks like we've got 14 of us so far here. Anybody else have any other questions?
Uh, when accessing Pearson, I haven't done it online yet, and I don't really want to test the system and cancel all my scores.
Exactly.
Uh, because Canvas is currently down, will it be back up by tomorrow so that I can still act? Do you know
Yeah,
if it'll
I
be back up by
expected it.
tomorrow?
They told me it would be back up by this afternoon, they thought, and I hope I am. But if we have anything like that, I'm going to push the deadline. If we have something that's due tomorrow, I'll probably go ahead and push it till Sunday just to be
Okay, I just wanted to make
done
sure that
with
I
it.
wasn't gonna start getting late penalties for it.
Yeah, no problem. In fact, if you notice that I don't set the dates back to Sunday, just send me a reminder, email or text message, preferably text message. That'd be quicker, and that way I'll just go ahead and do it. I just
Okay, thanks.
can't do it yet. All right, looks like we got more people coming in, and it is about time to start, so I should go ahead. All right. So last time we had actually finished chapter 7, and now I'm going into chapter 8, which is conservation of energy. So I've got to tell you a little bit about the whole paradigm here, which I've sort of hinted at it already with regards to chapter 7. With chapter 7, we jumped into this idea of work, and we took, for starters, a new mathematical technique that maybe you hadn't heard of before, but hopefully you had from trig or whatever, and it's a dot product. And I swear I haven't yawned at all today until now. So, anyways, but with that, we first introduced a dot product, and that dot product, I said, we use that in the physics and engineering world to pick off components of vectors that are parallel to one another. So, if you take the dot product of A and B, that's called A dot B. It's also called the scalar product of A and B. Then that turns out to be A, the magnitude of A, times B, the magnitude of B, times cosine of the angle between them when they're tail to tail. And if you drew a diagram on there making a right triangle out of one vector, then what you'd see is the other vector would be multiplied by cosine theta, so it gives you the component of A parallel to the other vector. So you can group it with, A being the component parallel to B, or you can group it with B being the parallel component of A. Uh, that's kind of a useful thing, and in fact, that's partly why we use it. There's another one called the cross product. We'll cover that later, and that actually picks off perpendicular components. So if you wanted only the component of a vector perpendicular to another vector, you would do the cross product, and that formula, oddly enough, instead of AB cosine theta, is AB sine theta. And the other thing about the cross product is that it is actually what we call a vector product. So when you take A cross B, you get a third vector that's perpendicular to both A and B, but its length is indicative of basically the component of A parallel, or excuse me, perpendicular to B times the magnitude of B. So that'll come in handy as well. But the main thing is once we had that dot product, we could then use that to define work because we wanted to only count the part of work that goes to moving the object. So we wanted the component of the force that was parallel to the displacement. Therefore, we took F dot D, where F would be the force and D would be like the displacement vector. And then we generalized that to consider it if you had just a straight line path, it wouldn't be that big deal, especially if the force always had the same angle with respect to that displacement. That wouldn't be a big deal. You could just do F dot D. But if, right here the force is this way, and then over here the force gets smaller and maybe is this way, and then it gets further along and it's longer, say, and a different angle, then you have to break that displacement vector or the path up into small pieces and just choose the component of F parallel at each one of those little points. To do that, we implemented the integral. So we ended up getting work is equal to the integral of F dot dl. That works great and we learned how to do it, but it was all leading up to this new idea where if certain things, if certain criteria are met, then we can do physics without vectors. And that is an easy deal and a big deal because it allows us to solve problems without the complexities associated with that, taking vectors, breaking them down into components and all that good stuff. And as long as we have a way of understanding it completely, then we should be able to figure out from the scalar quantities exactly what the vector quantities are. So that's where we're going in the big picture. And chapter 8 is sort of the culmination of all that. And then we'll continue to use that principle throughout the rest of the 2 or 3 semester sequence that is this course. So if you were taking this, for instance, at Virginia Tech or UVA or ODU or something, what you'd find is they'd have something like our 241, then our 242, and then they'd have like a 243. So it's a 3 semester course, and that third semester's basically modern physics. So it cover quantum. It would cover quantum mechanics and relativity and nuclear physics and particle physics and cosmology and neat stuff like that. And what you'd find out is some of that same stuff we're using today in chapter 8, we'd still be using in 242, and we'll still be using it again in 243. So I thought I'd start off with showing you what that big idea is. So let me go ahead and start by sharing my screen with you. I just want to remind you guys this is chapter 8, and it's called Conservation of Energy. So I'll write that down here. So that's what the chapter is called, conservation of energy. But I'm sorry, it didn't finish. I pushed the buttons, but it didn't seem to follow through with it. It's coming, I promise. Okay, so it's called conservation of energy. And what I wanted to tell you is there is an idea of a force being conservative. And it turns out that there's a mathematical theorem that we can apply, and you don't have to prove it. It's been done for us, so we know how to do it. The big thing is this. If any one of these things I'm getting ready to write down is true, then they're all true. So let me show you exactly what I mean by that. So if any one of the conditions below, oops, are true, then they all are true. So, condition one. Now I'm seeing f of x, y, z to try to point out to you that this is what we call a vector field. So it's an assignment to all points x, y, and z, a force f that is a vector quantity. And the statement that I'm writing here is f of x, y, z is a conservative force. And as you might have guessed, the word conservative suggests that it has some conservation law with it, and that's exactly the point. Is if you have a conservation law, it's more than likely a result of some kind of conservative force. Not always, but sometimes. So one of the conditions is F is a conservative force. Another condition, again, if any one of these is true, they're all true. Another condition is that the curl, or excuse me, yes, uh, del cross F of X, Y, Z, and this means is identically zero. And what I mean by that is whenever you do this operation, and you guys don't are not expected to know exactly what this operation is that I just wrote down, but if you do that operation, you could imagine you get some formula that involves X, Y, and Z. What I'm saying with this triple equal bar sign is that if that quantity is zero, period, it doesn't have any x dependence, y dependence, or z dependence, and you don't have to put in a specific value of x or a specific value of y or a specific value of z to get that zero, then it's what we call identically zero. So that's going to be true as well. And this quantity right here is called the curl of F. Specifically speaking, I will just show you quickly what it is. Del cross F is the determinant of a matrix in which I hat is the first row, I hat, j hat, and k hat make up the first row. The second row would be the partial derivative with respect to x. I'm abbreviating it by just writing that little backwards 6 with an x, but in reality, that should be something like the partial derivative with respect to x, something like that. Okay. The partial with respect to y and the partial with respect to z of f sub x, f sub y, and f sub z, meaning the x component of f is the uh, first entry in the third row. The component of f in the y direction is the second entry in the bottom row, and the component of f in the z direction is the third entry in the row. Okay, but that's how you'd actually go about computing that, and you can see that this is a little bit more than just multiplication. This is actually derivatives acting on a vector function. Again, not something that you're required to do. I just told you that for reasons that basically it makes you a little more knowledgeable when you go forward, and it won't seem like Greek and super scary when you do finally face it. So, what we've now found is that one condition is F is a conservative force. Another condition is that the curl, and that's what that's called, the curl of F, is identically zero. And then there's a third one that says if you do the work or calculate the work from A to B of f of x, y, z dot dl, it's going to give me some u of b minus u of a that is independent of the path of integration. So this is a pretty big helpful thing. It basically says, hey, if you need to calculate the work done in moving something from point A to some other point B, then you can do that calculation. And you could, for instance, do that calculation of that line integral along the path that you actually intend to travel. But according to this theorem, you can do any other path that might even be easier for you to solve. And not only that, the final answer is just going to be some function evaluated at B minus that same function evaluated at A. So if we can ever figure out what that function is, we don't even have to mess with the integral. We can just do u, that function evaluated at B, minus u, that function evaluated at A. So that's a really, really big deal. The next one is, now we're getting fancy. Notice I did not only an integral, but it's an integral with a circle on it. What does that mean? Well, that is a little symbol we use in vector calculus to say, hey, here comes an integral. It's technically a path integral, but it's a closed path. So I've got to integrate from some point in space. I can go anywhere I want, la, 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 long as I end up at the end being right back at that same spot. So if I do an integral over any closed path, then that integral of f of x, y, z dotted with dl will be equal to 0. So that's kind of a whole neat thing as well. It just tells us, hey, if do the work required to go from one point and do a lot of different things, but returns back to that final point, then the total work done will be 0. Okay. I can show you part of that being true just by if you imagine that some of the types of energy that a particle could accumulate when going along some path, one of which is kinetic energy, another type of energy is potential energy, which I'm getting ready to teach you guys. But the main thing is those things go and change. Potential energy can be converted to kinetic energy, and kinetic energy can be converted to potential energy, and all this stuff, especially through a cycle. But when you get back, all those initial conditions that it had when it first left that point will be exactly the same when it arrives. So this is, in some sense, the reason that if you can ignore air resistance, if you throw a ball up in the air, when it falls back down and reaches the same height that it was at when it left, in other words, it ends up back at the exact same spot, its velocity is going to be the same, or I should say its speed will be the same. Its velocity is actually different because obviously it was going up on the way up, but on the way back it was going down. So the velocity, that vector quantity, wouldn't be the same, but the magnitude of it will be the same. And as you know, I've made one of the comments about shooting up in the air. That's some of the things that some people do celebrating weddings and whatnot. If you actually shoot a bullet straight up in the air, there's some probability that bullet's going to go straight up and come right back down very close to where you are, and it could in principle hit you or hit one of the party goers, and that would be a problem. And the reason why it is a problem is because all you're relying on to slow that bullet down is air resistance. Now, air resistance would be significant with a bullet, and especially, firing it at the muzzle velocity of a handgun or a rifle or something like that. That's a pretty significant friction force. So it will be significantly slower. But you trusting that is sort of like saying I'm going to use a air-filled, if you've ever seen those little water wings that kids wear on their arms when they're swimming to learn how to swim. Well, imagine a life preserver made out of that type of material that you just blow up and use it as a life preserver. They exist and you can use it, but would you want to use one of those as a bulletproof vest? No, you wouldn't, but that's pretty much what you're doing if you shoot a bullet straight up in the air and, hope that it doesn't hurt you if it comes back down. That's what you're doing. So that's a instance where if you ignore air resistance, because air resistance is a non-conservative force, if you do ignore air resistance, then the force of gravity, which is a conservative force, does obey these principles, and therefore its kinetic energy, its state of being, when it leaves, will it be exactly the same when it returns. So it will be going the same speed when it returns. So that's another principle that we've gotten from this, all from the force being conservative. So again, if one of these are true, all of these are true. Now, in addition to that, there is a condition 5, and I'm going to use some fancy mathematical symbols. So if you guys go further into math, you'll have at least seen these before. But first off, I'll start off with a backwards upside down E. That means there exists. So there exists a scalar function u of x, y, z such that this is supposed to look like if you actually wrote in cursive such that, in case you're not that familiar with cursive, that's what such that would look like. So if you just tried to do ST, you would see this symbol looks like that. And that's what that symbol means. It just means such that. Such that F is equal to the negative gradient of U of X, Y, Z. In other words, notice I used the same symbol U that I used up here in condition 3, which says the integral of f of x, y, z dot dl from a to b is ub minus ua. That's that function that we're talking about. It's that specific function. It's called a potential energy function. Okay, so this is not only something that tells us that a scalar function exists, this is in some sense, a prescriptive method of getting the force back out of the actual quantity U. Not only that, now if you look at item 3 on this list, you can see that is a prescriptive method of figuring out what the potential energy function is. All you have to do is take the conservative force, calculate the work done from point A to point B, and then looking at the solution to that, recognize that it's some function evaluated at B minus that same function evaluated at A. So that actually gives you a way of figuring out exactly what the scale the potential energy or the scalar potential energy function is. Now, in addition to this, there is a another condition, and I don't really put this in the mathematical terms the right way, but basically, if you've studied differential equations, if you're in that class now, or if you've already had that class, you will have learned that there's, and I suspect by this point in the semester, you've already covered this material because it's normally like the second or third topic covered in differential equations class, an ordinary differential equation class, and they're called exact differential equations. So there is a tight relationship between forces or force fields that are conservative, such that the differential of that conservative force field is given by a very specific quantity, and it lends itself easily to what we call one of those exact differential equations. So whenever you have one of those exact differential equations that's like some function of x, y in parentheses times dx plus some function of x and y in parentheses times dy is equal to zero, the thing that you learn in differential equations is you take that function of x and y that's in front of the dx and you take the derivative of it with respect to y, and then you take that function in the parentheses in front of dy and you take the derivative of it with respect to x. If you get the same answer from those two derivatives, then that you've met the test that's required to show that this is an exact differential. And then there's a very specific process that goes into solving that differential equation. So that is something else that comes out of this theorem, if you will. It's just like I said, I can't really write out the terms of it specifically because they're quite convoluted. But the main thing is just know that it has something to do with that. I will tell you that df, if it's an exact differential, is the partial derivative with respect to x times dx plus the partial derivative of f with respect to y times dy. And in fact, if you had it, it was in three dimensions, it would be plus a partial derivative of f with respect to z times dz. But that's the main thing, the fact that you're taking the derivative of the same function in both of those terms in front of the differential. That's why you do the test. If you take the derivative with respect to x of the function that's in front of the dy, and you take the derivative with respect to y for the function that's in front of the dx, because what you're assuming is that if it is an exact differential, then the function in front of the dx is already the derivative of f with respect to x. So by taking the derivative with respect to y, you've now done the second partial of f with respect to x, then with respect to y. And if you do the same thing with the other one, then you're taking the second partial of f, which the first partial was already taken with respect to y, but now you're taking it with respect to x. And for the vast majority of functions, there's no difference between taking the derivative with respect to x first and then the derivative with respect to y and then doing it the other way. So that's what you're doing by testing whether the two are equal to each other. You take the derivative of the thing in front of the x with respect to y, and you take the derivative of the thing in front of the dy with respect to x. And if those two terms are equal, then what you've seen is, oh, they must both be a partial derivative of some greater function f that you're trying to discover. So, anyways, this is the big paradigm, and because of all this, anytime we find a conservative force, we can immediately derive a scalar potential and then use that scalar potential to solve physics problems. Okay. So that's what we're going to do, and I'm going to show you how to do it now, and I'll show you, for instance, in part 5, exactly how we use that. I will mention to you that this del operator, which for some reason I happen to know also in in Portuguese, is called nabla. I just happened to know a guy that lived in Brazil and learned Portuguese so he could teach physics in Brazil, and he found out that they call the del operator nabla, Nabla. I don't know why, but anyways, if you ever hear the phrase nabla, and believe it or not, I've heard it a couple times. That's why I always tell my students it. But if you hear that phrase nabla, it means this, what we call a differential operator. And what I mean by an operator is this this upside down triangle is meant to be written with a little space after it because it's meant to act on something. So whatever's on top of that red underline is what this operator is acting on. And to write it so that you understand it that way, we normally would take the I hat and put that in front because it's actually a vector differential operator. So it actually takes a scalar. If you do like I did in step 5, it takes a scalar function u and creates a vector out of it. The way it does it is you take whatever it's operating on, you take its derivative, partial derivative specifically, with respect to x. And notice I left that little space right there. Okay, that's because whatever's to the right of it would go in that spot. Now I'm going to say plus j hat partial with respect to y. There's that little slot again. Plus k hat, the partial with respect to z. And again, I'll put that little space there. Okay. So that's what that differential vector operator is. And there's pretty much three or four things that we actually do with it. We'll sometimes say something along the lines of the gradient of a scalar function is equal to the partial of f with respect to x I hat plus the partial of f with respect to y j hat plus the partial of f with respect to z k hat. This is called the gradient. And if you want to think about physically, what does it mean? Well, the gradient is it gives you the steepness of something. So you can think if you actually did the gradient of a topo map, it would give you the difference in height or the steepness, I would say, of the actual hill and going from one topo line to the next. That's sort of one way of thinking about it. Now, another thing you can do is you could also talk about the divergence. Ah, darn it. Sorry, got a lot of letters going on here. The divergence of a vector field. Again, a vector field just means it's a function of x, y, and z, but part of that function is in front of an I hat, so that would be the x component. And then another part of that function is in front of a j hat, so that would be the y component. And another part of that function is in front of a k hat, and that would be another component. And the divergence tells us how rapidly that function runs away from like the origin. But in this case, it would be written as del dot f, and that's called the divergence of f. And technically, what you do is you take the derivative of the x component of f with respect to x and multiply it by I hat. You take the derivative of the y component of f with respect to y and multiply it by j hat, and the partial of f with respect to, or excuse me, that's the fz. I really wrote that kind of ugly. Let me fix that. Again, I am not making you do any of this. I'm just giving you the formulas so that you could do it if you get so interested, and so that you won't be completely uh, shocked when you first run into it. And then finally, the last thing we have is that curl that I showed you already, and that is the curl of a vector field is del cross f, like that. And you'd have to do that determinant as I showed you above to do that. And I could write out the components of it. It's not something I want you to try to do. If you want to, I will gladly do it in a case by case basis with you personally, but I don't think there's any need for you to know how to do that at this point. The main thing is that's three of the major things that vector operator is used for, and one of them we are going to use specifically the gradient, and we are at least hinting to you that the curl and the divergence are things that are important. It turns out that if you want to solve for a vector field, some f of x, y, z I hat plus f of x, y, z sub y j hat plus f of x, y, z sub z k hat, if you want to solve for that vector field, it turns out that if you have the curl of that vector field and you have the divergence of that vector field, then you have enough to figure out exactly what that vector field is up to the addition of one constant vector. So that's the advantage of it. In fact, when we write out Maxwell's equations, which is what we'll do in 242, there's exactly four equations that are Maxwell's equations, and two of them are the divergence of the magnetic field and the electric field, and the other two are the curl of the electric field and the curl of the magnetic field. So it basically allows you to figure out exactly what the curl and the magnetic field is as a vector quantity. So now that I've given you all that stuff that's probably way more than you want to know, I'm going to now show you exactly how we compute a scalar potential energy function. So I'm going to turn to the next page. So I'll say how to determine the scalar potential energy function. So in order to have this, like it said in step 5, we have to have a conservative force. I will tell you that the conservative forces that we've learned so far are just the gravitational force. Both the weight, F equals mg, that's one version, but also the Newton's law of gravity, F equals g m1 m2 over r squared. Both of those are conservative forces and meet that criteria that's spelled out in item 2. In other words, if you took the curl of that function, you would get identically zero in the case of the Newton's law of gravity, but also in the case of weight equals mg. Uh, in the future, you will learn that Coulomb's law, which is just like Newton's law of gravity, but it's for the electric force, that one happens to be a conservative force as well because it looks just like Newton's law. So that one will allow us a scalar potential function as well. And in fact, that scalar potential energy function it turns out not to be exactly potential energy because instead of us talking about the force due to the electric field, we actually use the electric field itself, which is differed by a division of 1 coulomb. So we end up talking about the energy per coulomb, which is oddly enough called the volt. So the idea of voltage that you've already been familiar with, knowing that, for instance, a AA battery is 1.5 volts. That is the scalar potential for the electric field. Okay. All right. So now let me show you how to do this. What we're going to do is we're going to imagine a particle in a coordinate system like this. And let's say this particle right here has a mass m, and we're going to take it from point A. Let's say, I'll use this. I'll say this is point A, and it corresponds to x equals 0, y equals 0. And we're going to bring it up to this point right here, which this point is point B, which is the point x equals 0, y equals h. Okay, so I'm going to say that quantity right there is h. I should probably write that in purple since I started in purple. So this is the point 0h, which corresponds to x2, y2, if you will. So what I'm going to do is calculate the work done in moving that mass m from x equals, or excuse me, from y equals 0 to y equals h. So here's the big sentence that's most important. Uh, the scalar, oops, the scalar potential energy function is, I should say, the change in. The change in the scalar potential energy function I'm trying to erase something. Hold on. In moving from point, actually, I'll go ahead and abbreviate it like I did before, from point A to point B is equal to the negative of the work done in moving. All right, let's see, the negative of the work done. I'm going to change something. By the conservative force. So the change in the scalar potential energy function in moving from point A to point B is equal to the negative of the work done by the conservative force during that move. So if we look back at line 3 here, we're taking an integral from A to B and we're going to get some u of B minus u of A. And what I'm telling you is when you get that, that change in that work done is the negative of the change in potential energy. And that's the prescription of how we find a potential energy function. So with this case, what we're looking at is a particle of mass m having a force acting downward, and that force F is conservative, and it's given by negative mg in the j hat direction. It's negative because it points down. According to my diagram, y, the positive y-axis is pointing up, gravity points down, so F equals negative mg j hat is the actual force. So now what I'm going to do is calculate the work done by that force. Okay, that's the key thing is you got to calculate the work done by the conservative force, multiply that by -1, and then that will give you the change in potential energy. And by looking at that change in potential energy, you should be able to figure out what the function, the potential energy is. So let's do that now. So I'm going to go ahead and say work equals negative change in potential energy, delta U, or excuse me, I should say that the opposite way. So let me write it back the other way. We're going to say the change in potential energy is equal to the negative of the work done from A to B by the F conservative. Okay, so this is going to be negative integral from A to B of negative mg j hat dotted with, remember the formula for work is work equals the integral of F dot dl. Okay. So what I'm going to do is I am going to allow my DL to indicate which direction I'm integrating. So I'm going to say this is obviously going in the positive dx, or excuse me, positive dy j hat direction. Now, since I've chosen to show the direction of integration using my DL, that means I've got to go from low coordinate to high coordinate for the range of integration, which happens to be the same thing as A to B anyways. So it doesn't matter that I already wrote the A and the B there. I can just leave it as is. And when I do that, I now get, notice the negative inside with the negative out in front gives me a positive. It's going to be an integral from y equals 0 to y equals h. And now we're going to use the linearity of the dot product. Remember, the linearity of the dot product means you can pull all the scalars out to the left or to the right and then let the dot product just act between the vectors. So the scalars are the two minus signs, the mg and the dy, and then I'm just left with j hat dot j hat. And of course, we can compute j hat dot j hat. Does anybody recall what j hat dot j hat would be?
One.
Exactly, because the magnitude of j is 1, the magnitude of the other j is also 1, and the angle between them is 0 degrees, and all that gives me just 1. Okay? Now, not only that, the mg is really just a constant, so the integral of mg just becomes mgy. So we're going to say this is mgy, which, by the way, that is technically the function. You don't even have to do the limits of integration to see the function. That actually gave us the function, but I'm going to follow it out like I said I would. So this is from y equals 0 to y equals h. So that's going to be mgh minus mg0, which is just equal to mgh. Okay. But looking at that, you realize that the function u, which could be a function of x, y, and z, but in this case it just turns out to be a function of y, is in fact equal to m times g times y. So that is what our scalar potential energy function is. All we had to do to figure it out was, one, we had to make sure we had a conservative force. And the only reason you knew we had a conservative force is because I told you. Okay. You could actually go and do the cross product that I showed you in step 2 here. We could actually calculate that curl, and that would come out to be 0. Then you know that F equals mg j hat is or negative mg j hat is an actual conservative force. But once you have the conservative force, all you got to do is realize that the change in potential energy is equal to the negative of the work done by that conservative force. In so doing, we have now figured that out. Now, remember, step 5 here shows us that there exists a scalar function u of x, y, z such that f is equal to the negative gradient of u of x, y, z. So let's go ahead and close the loop by showing you that the force is actually what we think it is. So if I take and calculate the negative gradient of u, then that's going to be negative I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z. Now, I should tell you at this point, the partial derivative is literally like, remember when we did derivatives, when you first learned derivatives, you would say df over dx was f of x plus delta x minus f of x divided by x plus delta x minus x, right? Well, the only difference is the partial of f, for instance, with respect to x, would be f of x plus delta x y z minus f of x y, z divided by x plus delta x minus x. You see how you're just pretending like the other y and z are just constants? That's all we're doing. So if I look at this function and see that the only variable is y, then all the derivatives, with exception of the derivative with respect to y, is going to give me 0. So this differential vector operator is going to act on the potential energy function, which we found was m times g times y. And notice what you get. You get negative I hat partial of mgy with respect to x minus j hat. Notice I am distributing that negative through. J hat partial of mgy with respect to y minus k hat partial of mgy with respect to z is equal to. Now notice we're supposed to pretend y is a constant when we're taking the derivative with respect to x, and we're also supposed to pretend z is a constant when we're taking the derivative with respect to x. There is no z, but there's definitely a y, so we've got m times g times like 4. The derivative of mg times 4 is 0, so we get minus 0, and then minus j hat. This was technically I hat times 0, but now we've got minus j hat. Now, in this case, the x is supposed to be treated as a constant and the z is supposed to be treated as a constant, but there is no x and there is no z. The only variable in here, the only symbol in here is in fact y, and the derivative of mgy with respect to y is just mg, so I'm going to get negative j hat times m times g, and then I'm going to say minus k hat times 0 again. So lo and behold, the negative gradient of v is, or of u, excuse me, is negative m g j hat, which is exactly the force that we said it was when I chose to do this. Okay. So that is the big trick here, and that's the thing you're going to learn. And not only that, it's the thing that's going to continue to be used into basically the rest of your career if you go into any branch of engineering or physics. Okay. Any questions on that one? All right, so I just worked out, for instance, what the potential energy function is for the conservative force of gravity. I didn't do the general one, but I could do the general one as well. Remember, the force of gravity in general is not negative m times g in the j hat direction. It's actually g m m over r squared. And pointing towards the center of the earth, that sort of thing. So you could actually do it with that, and we'll do that in a little bit. But the main thing is that's the way we do it. We recognize that the change in potential energy is equal to the negative of the work done by the conservative force. In other words, we got to calculate the work done by the force itself, not by someone fighting that force. Okay, so that's why the force was negative mgy, whereas the force we'd actually apply to it to move it would be positive mgy. So now that we have that, let's go and try to solve some physics problems. Oh, another conservative force, for instance, is the F equals negative kx, Hooke's law, in other words. We knew that because we already worked out that the potential energy for that is 1/2 kx squared. So that's it as well. That is, in fact, another conservative force is F equals negative kx. So now that we have all that, we can try to solve some physics problems using this concept. But what you got to remember is ultimately we're going for a conservation law in which energy can neither be created or destroyed. And that energy is what we call mechanical energy. And we normally base that in more or less two quantities. One is potential energy, which is the potential to do work. and the other one is the kinetic energy, which is the energy of motion. And the way your book mostly solves such problems is by using this idea: delta U, the change in potential energy, plus delta K, the change in kinetic energy, is equal to zero. And this really works. Another way you could write that, for instance, is remember the delta always means final minus initial. So this would be U final minus U initial plus K final minus K initial is equal to zero. And from that, you can see that U final plus K final is equal to U initial plus K initial. So that's another way you could write it as well. And I usually go a step further in that when I'm doing this, I can only address conservative forces. I would ideally like to be able to solve without vectors, solve problems that involve non-conservative forces. So forces like friction, air resistance, that kind of thing. So what I've done is that, and I've been doing this since I was, literally an undergraduate myself. I came up with this on my own, and it's served me well. So instead of using this form or this form, I sort of use a combination thereof. What I do is I say U initial plus K initial plus work in is equal to U final plus K final plus E. Well, I'll go ahead and do it the symmetric way, plus work out plus E loss. Now, there's not, quote unquote, a definitive definition of exactly what I mean by work in, work out, and E loss. It's just basically any non-conservative force you use, or any non-conservative force an object is subject to, you can always calculate the work done by that force. And the work done by that force is basically being stolen from the total energy that you have in the system. So, in the case of initially, you could imagine, for instance, a father pushing his child on a sled at the top of a mountain. If the father gives the child a slight push, maybe over a 3 meter distance, then you could calculate the work done by that push, and that would be actually adding energy to the system. So I put work in on the left hand side because that means you're going to have more energy than just the initial potential energy, which is, mgy, plus the initial kinetic energy, which is 1/2 mv squared that you have because the actual sled is moving and therefore has a velocity. But you have an additional amount of energy given by the work put in. And then at the end, when you get to the bottom of when the kid gets to the bottom of the mountain, then they've exhausted their potential energy. The I that was so high before because you're up at the top of a mountain, the UI has probably gone to zero if you're actually at the bottom of the mountain. And now the kinetic energy is the lion's share of the energy. But if there was any friction on the way down, you probably would calculate the work done by friction and call that E loss. That's why I've got E loss on the right hand side. And when you get to the bottom of the hill, maybe there's some kind of mechanism that someone made so that you could save the kids from, being pushed down, and then they get at the bottom of the mountain and they're going so fast that they end up shooting across the parking lot and getting hit by a car or something. You wouldn't like that. So you put up let's say a big piece of plywood with a spring-loaded system behind it so that when the child hits the padded plywood, they're going to compress a spring, and that's going to slowly, without much force, bring that actual sled and child to a stop. Well, in that case, the actual sled and child are doing work on a spring given by 1/2 kx squared, where x is the amount the spring compresses. So that's sort of a perfect problem gauged specifically to fit this version of the conservation of energy equation. But as long as you account for each type of energy being created or taken away by some work done by a non-conservative force, it doesn't matter where you put it in. You could put it in and work in or what else. It doesn't matter. You could even add a term on the left-hand side that would say EN, and you could stick that in there. The important thing is just you keep count of every type of different amount of work that could be done, and you put it in the appropriate slots. If this is an energy that makes the energy initially larger than it would otherwise be, then it should go in the work in slot. If it's energy that's being stolen in between the initial position and the final position, then you should put that in the E loss or the work out slot, or maybe both, right? You wouldn't use the same one twice, of course. That would be double counting the energy loss, but you could still use two different terms for various things. Maybe you have a friction force due to just friction, then you have work done against air resistance. Both of those could be added up and put in E loss. You could also say that you're compressing that spring-loaded padded plywood with work out being 1/2 kx squared. So those are various ways you can do it. I'm going to start off with example 8.1 real quick just to show you what we're saying here. I know you don't have access to Canvas. If you have access to the mastering site, then you can pull the book up there. But example 8.1 is as follows. It says a 1,000 kilogram roller coaster car moves from point 1 in figure 8.5 to point 2 and then to point 3. A, what is the gravitational potential energy at points 2 and 3 relative to point 1? That is, take y equals 0 at point 1. And B, what is the change in potential energy when the car moves from point 2 to point 3? And then C, repeat parts A and B, but take the reference point y equals 0 to be at point 3. So let me start off by drawing a figure. So our figure should go like this, and then it goes up a hill, and then goes down a hill to even lower, and goes like that. Uh, what we're going to do is we're going to call this point 1. We're going to call this point 2, and I mean the point at the top of the hill on the roller coaster. And we're going to call this point 3 at the bottom of the hill. We're going to add some measurements on here so we'll have some idea of what we're dealing with. It turns out that this height from here to here is 10.0 meters, and this height from here to here is 15 meters. I don't have to put a dot 0 with the underbar there because both the 1 and the 5 are sig figs. And they're saying Y up that way. Okay. We have a little roller coaster car right here. Okay. We do know the mass is equal to 1,000 kilograms. And now we have the figure. So we're going to say A is supposed to be, what is the gravitational potential energy at 2? So U at 2, and I'll say WRT 1. And then we also want to know the gravitational potential energy at 3. So U at 3, WRT, that means with respect to 1. So that's what we're asked in part A, which implies 1 implies y equals 0 at 1. Now for part B, they ask specifically what is the change in potential energy as the car goes from point 2 to point 3. So delta y from 2 to 3, which I would normally call delta U 3 comma 2 because I normally write final minus initial like that. They want to know what that is as seen from part A. And then part C, repeat by using at with respect to 3. Okay? So our solution is going to make use of the fact that U is equal to M times G times Y.
A
And we're going to,
question.
yes, go for it.
Isn't C just going to be the negative of A? Like the answer we get for C, isn't it just going to be the negative of A?
Yeah, it looks like it'd be pretty close to the negative of A. Yep. That's sort of the point of this problem is what's ultimately going to matter when you're dealing with potential energy is not the absolute amount of potential energy you have, but rather the change. And what you'll see is even though the final potential energies will be different for the two answers, the change in potential energy is going to be the same for both answers. In other words, everything we do in part B will give exactly the same answer in part C when I'm talking about the change in potential energy, but not the total potential energy. That's sort of like that idea where I told you that if you have the curl and the gradient, excuse me, the curl and the uh, divergence of a vector field, then you can solve for the vector field up to an additive vector. That additive vector doesn't matter because all the important things that you do come from taking derivatives. And when you take the derivative of an additive constant, it's just going to be zero. The same thing's happening with this potential energy. An additive constant is not going to matter at all. So, but yes, you're right. And good seeing that, Jaden. So let's look at this. The potential energy U at 2, so U at 2 is going to be equal to 1,000 kilograms times 9.80 meters per second times, in this case, since we're calling y equals 0 at position 1, then the height is just going to be 10.0 meters. So we get 9.8 times 1,000 times 10. So this would be 9.80 times 10 to the fourth joules. Everybody follow what I did there? U at 3 is equal to 1,000 kilograms times 9.80 meters per second. Now, in this case, the y value is negative 15 meters. So we get 1,000 times 9.8 times negative 15. So 1,000 times 9.8 times negative 15 gives me 1.47 times 10 to the fifth joules, and that answer is negative. Okay, so that's our two potential energies. I should probably make this negative a little more obvious by putting it like this. And what I'm going to do is I'm going to circle this and this. And I left a space so I could write equals U at 2, and this is equal to U at 3. So that's part A. Now, part B, they want to know delta U from 2 to 3, which I said I would normally call delta U 3, 2 because it's final minus initial. So I would say U at 3 minus U at 2. And that's going to give me U at 3 was negative 1.47 times 10 to the fifth joules minus, in this case, it's going to be positive 9.80 times 10 to the fourth joules, which gives me a net change of 1.47 minus 9.8 times 10 to the fourth. Ooh. Well, it's not letting me take the function. Okay, hold on a second. My calculator doing something crazy there. So answer minus 9.8 times 10 to the fourth. That gives me negative 2.45 times 10 to the fifth joules equals delta U 3 comma 2 like that. So that's the change in potential energy and going from position 2 to position 3. Now for part C, they want us to repeat all of that that we did in A and B basically for part C. So here's part C. Uh, let's say U at 2 with respect to 3 is going to be equal to 1,000. I'm going to leave the units off this time just to save some space. 9.80. And this time, the height difference, in other words, the Y value, is actually for position 2 is going to be 25 meters. So when I multiply 1,000 times 9.8 times 25, I get 24,000, or excuse me, 245,000, which I could write as 2.45 times 10 to the fifth joules. Now I'm going to do U at 3 with respect to 3. That's going to be 1,000 times 9.80 times 0 meters. And that, of course, gives us 0 joules. So now I can say delta U 2 to 3, which is equal to delta U 3, 2, is equal to 0 minus 2.45 times 10 to the fifth joules, which gives us negative 2.45 times 10 to the fifth joules, and that's equal to delta U 3, 2. So do you see that I think you were talking earlier about the U at 3 versus the U at 3, but in this case, what I was replying about was the fact that the change in potential energy from position 2 to position 3, no matter which coordinate we used as y equals 0, no matter which point we used, we still got the exact same change in potential energy, specifically negative 2.45 times 10 to the fifth joules. Does that make sense to everyone? Okay. Anybody have any questions on that? Now, your book goes on to talk more about that so you'd understand. And in this case, it goes back and rederives the formula for the kinetic, I mean, for the work done in compressing a spring. And since we already know what that work done in compressing a spring was, it was 1 half kx squared, then we know the potential energy U is equal to 1 half kx squared. So I just want to take a second and draw a line and write down what we have. In addition to the red boxes that I have at the top of this page, which are 3 different ways you can solve conservation of energy problems, I'm going to go ahead and give you a couple forms of potential energy. So U, oops, it tried to make my writing neater than it was. U for gravity, I'm going to say a lowercase g, and that should just remind you that, oh, we're meaning the gravitational force when we use m times g. Okay. In that case, you're talking about potential energy when you're near the surface of the Earth. So your distance from the center of the Earth is well, it's very, very close to the radius of the Earth, not a significant fraction of the radius of the Earth farther or closer to the center. So in this case, the potential energy is going to be m times g times y. There also happens to be U, the potential energy associated with the spring. So I'm going to call that one U sub k. And in that case, that one's 1 half k x squared, where k is a spring constant. Now, in addition to that, we also have a kinetic energy, and k is equal to 1 half mv squared. Yes, go ahead.
Why isn't it negative half for the spring?
Oh, it is actually turns out to be positive. Let me go ahead and show you the derivation for that again, since you asked. I'm going to go ahead and box these off so you'll know that they're important. And we're going to do another one using Newton's law of gravity, but right now I'll get that. So when you actually calculate the change in potential energy, what we're going to do is we're going to assume that Hooke's law is a conservative force, and that's because I already know that it is. Okay. And there's our X, there's our Y. We're going to say that there's a spring connected to this wall right here. And then I'm going to say that maybe we put just a box right here just to give us something physically to think about as opposed to just thinking about pushing a spring to the left and to the right. So the delta U is supposed to equal the negative of the work done by the conservative force. And that means negative integral F conservative dotted with DL. Okay. So negative was already there. We're going to take the conservative force, which is negative KX, and it's going to point in the I hat direction. And this time I'm going to use the DL to indicate exactly which direction I'm going. So I'm going to imagine stretching the spring in this case. I could imagine, well, actually, no, let me go ahead and compress the spring. I'll compress the spring, in which case the DL is going to be negative DX I hat. Now, I've chosen the DL to indicate the direction of integration, so that means I've got to use the positive coordinate direction for the range of integration. So I'm going to go from negative x to 0. In reality, we're actually integrating from 0 to negative x, but since I chose to do so with the negative dx by saying the dl points in the negative direction, then I have to put the positive coordinate direction on the integral. So that's why that's that way. I'll show you again with it doing the other choice in a section, and you'll see you still get the same answer. But let's go ahead and continue with this. Now, we're going to go ahead and use the linearity of the dot product, which means we can bring all the scalars out in front, and I'm going to pull the constants out in front. The constant so far is just the negative signs and the k. So I've got a negative times a negative times a negative. That should give me a negative and then a k, and then the integral from negative x to 0 of x dx, and then I hat dot I hat is what the dot product is. And of course, we figured out that that's 1. The integral of x dx is 1 half x squared. So we're going to get negative 1 half k times x squared. And I'm going to evaluate that from negative x to 0. So that's going to be negative 1 half k. Now I'm going to say 0 squared minus negative x squared. And you can see that that negative inside the parentheses, when you square it, it's going to become positive. But the negative out in front from the subtraction is going to cancel out with the negative out here. So I get 1 half k x squared. So that's why it became positive. I can do the same thing. Let me show you the same integral, but choosing to indicate the direction of integration with the range of integration instead of with a DL. So just so you'll see, delta U is equal to negative W conservative, which equals negative integral of negative KX I hat dotted with, this time I'm just going to let DL point in the positive coordinate direction, which is DL I hat. And in doing so, I've now got to use the limits of integration to show exactly which direction I'm going. And in this case, I'm starting at 0, but I'm going to negative x. So I get a negative times a negative is a positive k integral x dx I hat dot I hat, which is 1. And this goes from 0 to negative x. So I get 1 half k x squared evaluated from 0 to negative x, which in this case gives me 1 half k times negative x squared minus 0 squared, which gives me 1 half k x squared, because again, the negative is inside the parentheses and it's being squared. Does that make sense?
Mm, no, because the negative x being the positive one doesn't make sense because it should, by definition, be lower than the zero.
So that is the case when something is linearly related to the x coordinate, but when it's a square or a fourth power, in other words, an even exponent relationship to x, then the fact that you go to a negative quantity or positive quantity doesn't matter, just because the square or the fourth power or the sixth power or the eighth power is always going to cancel out that negative.
Okay, but both ways equals half kx squared.
Yeah, whether you're compressing it or stretching it an amount x, it's always going to be 1 half kx squared. Those are good
Okay.
questions. It's good that you're thinking that way. So don't beat yourself up for getting the answer wrong. That's exactly the way you need to be thinking. Is this doesn't make any sense, and let me see why. So yeah, keep that up. That's not a bad thing.
Okay.
All right. All right, so now I'm going to do really quickly. I don't even know if I have time. So if I run out of time, you guys are free to go. I only got like 3.5 minutes left, but I want to go ahead and find out the potential energy for Newton's law of gravity. I'll let you look at my examples on my YouTube channel by looking at the links in Canvas when that ever opens, and we'll probably hit a couple more later. But I'm going to put some links on there that maybe some links that aren't already there in your module. So let me go ahead and start this Newton's law of gravity. So let's say we have a planet of mass m, and I have a radius r for the planet. Now, this could be the Earth's radius and therefore the Earth's mass, but what we're going to have is a mass m, lowercase m, that I want to move to some distance, and you can go any passable direction that you want, but the main thing is I'm going to pretend like it's a very, very far away distance. Okay. And in fact, that distance is going to be, uh, let's say, just plain R2. I'll just call it like that. Well, work, or excuse me, delta U is equal to the negative of the work done by the conservative force. So that's the negative integral. The law of gravity says that the force is equal to GMM over R squared. And in fact, it points radially inward. So there's a vector specifically for that. And I put a negative on it like that because it points in, and then I put a r hat right there, and that is the radial coordinate for spherical coordinates. So that's actually what that little unit vector is. That's what we're going to use. That therefore the force is negative g m over r squared r hat. There's the conservative force dotted with. Now, in this case, I can use I'm going to go from R to R2, and that's in the positive direction. So it doesn't really matter in this case whether I choose the DL to show the direction or the range of integration, because both of them are in the positive direction. So I'm going to go from R, the radius of the planet, to R2. Notice both of them point in the positive coordinate direction. That's why it didn't matter which one I did, because they're both going to come out the same way. With that in mind, I get negative times a negative is positive. I also get GMM like this, and I get the integral from R to R2 of, in this case, it is dr. Well, let me write it a different way. I'm going to write it R. Whoa, Nelly. I'm going to write it R to the negative 2 power times dr. times r hat dot r hat. And even not knowing anything about r hats, you know that's still 1 because they're both unit vectors because they have hats and they're identical. So the theta has to be 0 degrees. So now we can take the integral of r to the negative 2. That becomes negative 1 over r to the negative 1. So I'm going to change this quantity to negative g m m. Now I'm going to take it to 1 over r, and I'm going to go from R to R2. So that's going to be negative G M M times, oops, this one's supposed to be R2 up here, times 1 over R2 minus 1 over R. Now remember, R2 is actually larger, so this subtraction actually gives us a negative quantity. Because R2 and being bigger and than R is going to be like 1 over 10 minus 1. And 1 over 10 minus 1 is clearly a negative quantity. But the main thing that you see here is whatever distance you have, you're going to get U for this potential energy function is just negative GMM over R. So that's the new potential energy function that we'll use for R. Uh, let's say for H on the order of R greater than R, the radius of the planet. So if you're dealing with something that might go a whole 2 Earth radii from the center of the Earth, or 1.5 Earth radii from the center of the Earth, or something like that, then you have to use this potential energy function instead of MGY. So you guys are free to go. Thanks for coming, everybody. I'll wait till the last of you leave, but I'll go ahead and change those homeworks too, so don't forget that. And have a good one. Make sure you chat at me your first and last name if you haven't done so already.
Can you go back just one? Because I think I missed something
There you go.
in that last. Thank you.
You're welcome.
Perfect. I'm caught up. Thank you.
No problem. Have a good one, Jaden.
You too.
Ian or Bryson, any of you have any questions? You can also type in my chat, Ian, if you want to. I see it looks like your audio is having a hard time, but you're welcome to type in my chat. All right. How about you, Bryson? You have any questions? All right. Looks like neither of those folks might not be there, so I'm going to go ahead and call it a day, unless I see anybody type some chatting beforehand. Does not seem to be the case. Remember, everybody, I'm going to go ahead and upload these notes to my Google Docs drive, which you have access to through going through My Documents, or I think it's called Useful Documents and Links in Canvas. So there's a link to that where you can find it. That's where the actual notes will be, and they're listed by the day's date. So, for instance, ours will have a little code that says PHY241N02B space 10202025 because it's 10/20/2025. Additionally, the actual video that I post on YouTube will have that code in it as well. So if you're looking for the code, or if you're looking for the video, you can go to my YouTube channel and don't push on the search at the very top, but the search down below the picture of my goofy dog smoking a ciggy, and do the search there, and just do a search for 10202025, and that'll pull up this video once it's been posted. So have a good one, everybody. Thanks for coming. Bye bye.